title of my talk is very generic, but the idea that I want to give in this talk, well, there are two ideas, two key points that I want to make in this talk. The first is that we need to understand the overall history of the universe in order to understand the distribution of life in the universe. We don't know anything, of course, about the distribution of life, but that's what we would like to learn. And we cannot neglect the overall history of the universe if we want to do that. And the second thing, the second key point that I want to make is that this thing, understanding the overall history of the universe, is also relevant for SETI, for the chances of success of SETI. So let me start with the big picture. I have a background in cosmology, so I would like to emphasize that we know a great deal about the history of the universe. We know that the universe that we can observe has been evolving for 13.8 billion years now. And there is one interesting thing that we see just by looking at, a very simplified history of the universe. And we can see by eye, by this picture, by this cartoon picture, that the universe didn't stay the same over the course of these 13.8 billion years. So there is a history of the universe. And that's really interesting, not just for cosmology, not just for understanding what happens in the universe, but also, as I will point out, to understand life. But the overall feature that we see here is that there is this trend in the evolution of the universe that goes from a past where the universe appeared to be very simple, very smooth, and very close to equilibrium in a sense, at least superficially, but I will say something more in a moment. And then as time goes by, as time passes, the universe appears to go towards complexity, towards clumpiness, structure, and disequilibrium. Okay, so this is already very interesting, but what we want to know now, since we are talking about SETI and astrobiology and life is the universe, is how life fits in this picture, and how typical is it? Is it just a fluke event, just a random event that happened very rarely in the universe, or it's something that happens frequently? And when you look at this picture as a physicist or as a cosmologist, it's very interesting because if you know the initial conditions, if you know what happened at the beginning of the universe and you know what's going on after that, you can actually predict a lot of things. And if you are a cosmologist and I tell you that there are fluctuations in this primordial plasma here, very hot and dense plasma, and I tell you that there are fluctuations of a given size, it's easy to predict that after some time there will be stars and galaxies and so forth, okay? It's very simple. Even if you didn't see any star in your life, you would be able to predict that. But for life, things are very different because there is no way to do a prediction like that from first principles, okay? So that's why we have to keep into account a more broad, more complex scenario. But let me emphasize a few points. When you look at this thing here, the appearance of life, even if just on one planet, it's kind of a weird thing that you have to explain. And why is that? Because compare this to another picture where the universe has been existing forever and it's always been like we see now. For example, what the old steady state model was claiming, okay? In that case, you have an eternity to produce anything, basically, and you can produce, of course, I mean, explaining life is much less difficult than in a universe like that, where you only have a finite time to produce life, okay? And the other thing is that to produce life in an evolving universe, you have to first do a number of things. You have to do a number of steps. And all of these steps that I emphasized here, that I listed here, are relevant not just for astrophysics, but they are relevant for life, okay? You have to, first you have to create nuclei of the light elements in the early universe. Then you have to have star formation. Then stars will produce other heavier elements. Then you have to do galaxy formation and mergers of galaxies, because you have to have large enough galaxies in order to have a metal enrichment in the galaxy. Otherwise, there's nothing like that going on. You have to do metallicity increase in galaxy. You have to form organic molecules in interstellar space, probably. Then you have to form planets, and you have to carry water on these planets, and then eventually you may have the first microorganisms and perhaps complex organisms and perhaps intelligence. Okay, there are a number of steps. So it's really you really need a historical perspective in order to do all of that. But you also need to understand the physics behind that. And the physics behind that is very interesting, because what actually happens in an expanding universe is that all of this is possible because there is the expansion of the universe. Because expansion drives disequilibrium. So if you look at this picture here, it seems counterintuitive, because you have something very simple here and something apparently very complex here. And it seems to go in the opposite direction that we are taught usually. It seems to go against the second law of thermodynamics in a way, because you would expect that simplicity is more likely than complexity. So you don't explain, if you look at this picture, it seems a bit strange, but there's nothing strange if you take into account that the universe is expanding. And because the universe is expanding, what happens is that you have two typical rates. One is the expansion rate, tells you how fast the universe is expanding, and the other is the interaction rate of anything that happens in the universe. So any reaction, all of these processes are governed by some rate. And the interesting thing is that the rates go in a different way, scale in a different way with density. And because the density of the universe is decreasing, sooner or later any process will go out of equilibrium. Okay, it starts with a very rapid rate and it keeps things in equilibrium, but then as the expansion goes on, anything goes out of equilibrium. Okay, and so this is the first really non-trivial thing that I think we have to know about the overall history of the universe. It's the overall history of the universe and the expansion of the universe that allows this equilibrium to take place in the universe. And the other thing is that if you look at entropy, and then this is the standard textbook picture that we learn in undergrad school about entropy, is that if you have a gas in a box and you start from this initial condition, you expect that the evolution is like that, okay? You start from clumpiness, and eventually you end up in a simpler state with higher entropy, where the molecules are spread around all over the box, okay? But this neglects gravity. If you have gravity, in fact, you have exactly the opposite behavior, because if you have an almost uniform gas with some dishomogeneities, the evolution goes in the direction of more clumpiness. Okay, so the fact that the first picture looked a bit puzzling is because we were not taking into account expansion, and we were not taking into account gravity. And if you take into account both things, actually gravity increases clumpiness in the same direction of the growth of entropy. Okay, so this is really beautiful, because it explains why our universe allows for complex structure to emerge spontaneously and to have more complexity as time goes on. Okay, and of course all of this is absolutely essential for life. If you think about the simplest thing you can imagine, okay, so a planet like ours with life on it and photosynthesis perhaps, or whatever process you may imagine, it's basically a process that thrives on this equilibrium. And the reason why it takes place is because you have a source of energy, but not simply energy, but low entropy energy. You have a lot of high energy photons with low entropy from the sun coming to Earth, which is at lower temperature, doing its things, and then putting back higher entropy, low energy photons in space, which fortunately is empty and cold. Otherwise, this wouldn't work. Okay, so you really have to have this thermodynamic machine, so to speak, where you have two sources: one high temperature, low entropy, and the other low temperature. And life operates between these two temperatures. Okay, and this happens because of what I said before. Okay, this is really interesting, and you can complicate these things immensely, but basically the idea is always the same. Okay, you can add instead of simple life, you can add more complex things happening. This is a beautiful paper by Frank Clayton and Alberti. People are starting taking into account thermodynamics when dealing with life. And of course, technological civilization is just one of the aspects of an overall process, which is basically the idea that you have to maximize the rate at which you produce entropy. Okay, that it's simply life. It's simply an efficient way of producing entropy. It's more efficient than non-living processes. Okay, so I think this is interesting because it has an interest for big history, it has an interest for physics and cosmology, and it has an interest for astrobiology and SETI, and I think it's really time to start thinking about things in this way. Okay, so of course there is an even bigger picture, and I won't say too much about this, but if you think about the future evolution of the universe, what's going to happen, we are not sure, but it may be that the universe is evolving towards a heat death, where the universe will be cold and there will be no structure because the universe will keep expanding forever. And this is even more strange, okay? Because if this is the case, then it means that everything that we are witnessing now is just, a very fleeting, passing occurrence in the history of the universe, because you will have billions and billions and billions and billions of evolution where nothing will happen because there will be a thermodynamic death. Okay, everything will be at the highest entropy, and there's nothing to do anymore. Okay, so this is interesting again, because if you take into account this picture, it seems something that you should keep in mind, that everything that we are observing is very untypical over the entire history of the universe. Okay. So now let me say just a few things about the connections within this historical perspective about the time issue and astrobiology and SETI. The first thing is I'm really interested in this idea about when the universe was habitable, not just where the universe is habitable, because everybody takes a lot of interest about finding habitable planets in habitable zones and perhaps habitable regions in the galaxy, and there have been a bunch of studies about that. But I think that an equally important aspect is when the universe became habitable, because of course what we saw before tells us that the universe was not always suitable for life. There's only an intermediate time when the universe is suitable for life, and we have to take into account that. So for example, one thing, this is from the famous Lineweaver paper, one of the first papers about galactic habitable zone, where you can see that there is the location of the sun in the galaxy, which is roughly where you expect to have habitable planets in space. This is a galactocentric distance, but also there is a time axis that people sometimes neglect, where actually Lineweaver was finding that you would expect the appearance of life to be distributed roughly as a Gaussian over the course of the history of the galaxy. So it's not a uniform probability of having life in time in the galaxy, because there are a number of things that have to happen before you have planets, you have molecules, you have environments which are conducive to life, okay? And this is for any life. The previous picture was for complex life. And so along this line, I've been doing a bunch of studies about what are the effects that can contribute to the overall habitability of our galaxy over the 10 billion years of history of our galaxy. And of course, there are many factors that people didn't take into account. One factor that we did take into account in recent papers is the history of our supermassive black hole at the center of the galaxy, which has a global effect on the entire galaxy, or a larger effect, of course, in the bulge. And as we know, it used to be an active source of a large quantity of ionizing radiation that can have some impact on life. And so, for example, here we studied the mass loss, the atmospheric mass loss of planets at given distances from the center of the galaxy with time. And of course, this is only one possible impact on habitability, because you can have other impacts from, for example, from harmful ionizing radiation, but arguably you may even have biogenic effects. Okay, so it's really a large topic that we're just started investigating. Okay, let me say just a few things before ending this talk about why this is relevant for SETI. We already saw in the talk by Claudio Grimaldi before that actually it's very interesting to take into account the fact that the light crossing time of our galaxy is just 100,000 years. Okay, so Claudio already showed you what is the impact of that for SETI. I want to show a slightly different take, which is taking into account the time issue, the temporal evolution. Okay, because let me rephrase what Claudio already said with a slightly different scheme. Basically, you have a signal, you have a civilization here sending a signal either intentionally or not, we don't care, in the galaxy, and we receive the signal today. But in order to receive the signal today, we have to have a very strong causal constraint. The signal has to be emitted at a very specific time, which depend on the distance of the civilization. Okay, and if you also model this with a two-parameter model, where you have the communicating lifespan and the time when the communication begins, you see that it's very unlikely that you receive anything unless there is a strong correlation between these two quantities, which are a priori uncorrelated. Okay, you wouldn't expect that the time when the civilization starts to communicate is correlated to the length of communication. Okay, they are uncorrelated, but you can only detect those which are very similar. So this either means that a civilization has to be very, very long-lived and communicating for a very long time, or it has to be starting communicating almost at the same time as we started making observations. Otherwise, you wouldn't get anything. Okay, so I hope it is clear, because I think this is a very, very profound issue, okay, which was neglected until now because people were using a Drake equation, which in fact only works when you have stationary probability of signals. Okay, but if you have an evolution of the probability of signals over time, then things changed dramatically. I won't go into detail because I'm almost over time, but let me show you a simple simulation that I did in a paper some time ago, where I show you that if you take the Drake equation and you compare this with a number of different distribution of the appearance of civilizations in the galaxy and the duration of their communicating history, then you get very different results in terms of the actual possibility of detecting these signals, okay? Because if you imagine that you have a number of civilizations spread over the entire history of the galaxy, then you only get some of them, and the way that the distribution is made in time gives you completely different results, okay? So this is the take-home message. You have to take into account the temporal aspects. So you have to take into account history, okay? So let me just summarize what are the main points. The fact that we live in an expanding universe introduces a historical element in our description, and the appearance of life has to be explained taking into account the temporal factor. And this is very different from what happened in a universe which is always the same, like in the an old steady state model. The other thing is that not all epochs in the universe are equal. Okay, habitability has most likely changed in time. There are a bunch of papers that show that actually the habitability of the universe increased in the past over time, but it will decrease in the future probably. And this is just a new paper that I want to point out that we did with Milan. It was just accepted by the International Journal of Astrobiology, when we make exactly this point that Copernicanism works in space, but it doesn't work in time, because our epoch to some extent is special in the sense that it's very different from all other epochs in the universe. And it makes sense to speak of cosmobiology, so not just astrobiology, but also cosmobiology in the sense of exploring the relation with the overall conditions of the universe and life. And this has important consequences for SETI and for explaining the Fermi paradox and many other things that I will not go into detail, but you can ask me if you want. Okay, thank you.
time for a quick question. Lady in the back.
You mentioned that history should be defined as one of the indicators driving the characteristics of the extension of life that goes beyond the linear kind of quick view or quick indication understanding of life. When considering the signals and which you want to integrate time aspects to it, how do you describe history as non-linear when you want to go beyond the linear aspect of time?
This is so the question, I guess, is how do you describe the history of, for example, civilizations over the history of the universe, if you want to not just use a uniform distribution? And the answer is that we don't have any deterministic a priori way of doing that. Actually, I'm fascinated by the thing that there is some mild determinism in biology, because I think this is a really interesting point, but I don't think that right now we have a model that tells you what you should expect. So the only thing I can say is we can do that in a phenomenological way. We can just choose a number of different plausible models and see how they compare and see what is the result that they give you when you do simulations and what is the outcome of that. But certainly a far future goal would be to try and produce some plausible model of how the distribution in space of time of life in the universe can be. I have no answer to that.